Alright guys, I'm going to talk a little bit about something called freefall. So far in this course we've been talking about things moving left and right in the x-axis. So when we're talking about accelerations, or we're talking about things moving with speed or velocity or displacement or what have you, we've really only been talking in the x-axis for the most part. Most of our problems have involved that. We haven't talked about going up and down. Going up and down is no different than going left and right. What I'm saying is all of the equations are the same. So the good news is that no new math, no new equations for going up and down. The bad news is that some sort of tricky things can happen when we're going up and down. And so what I found is when you have problems where things are moving up and down, it's crucial you draw a good picture. It's crucial that you make a chart. It's crucial that you define which way things go using negative and positive. And we'll talk about that here in a minute. Now, first of all, you guys are probably, I think you've already learned that on Earth, the downward acceleration is this value, 9.8 meters per second. We call this little g. This has several names. This is the field strength of gravity on Earth or near Earth. Little g is our field strength. There is a gravity field. How do I know this? Well, I can take things and I can release them, and they're going to accelerate a certain way. This is called a test mass. If I take my test mass and I let it go in this field, it will accelerate in the direction of the field, and everything's going to go down towards the center of the Earth. We call this gravity. I like to call it the force due to gravity. This is not a force. This is our field strength. This is an acceleration. Notice meters per second squared. What does this mean? This means that if you let something go, it will accelerate at that rate. Anything and everything will near the surface of the Earth. I find that students don't really understand what this means. This means that after 1 second, you will be going 9.8 meters per second. After 2 seconds, you will be going double that. 2 times 9.8 is 19.6. After 3 seconds, it'll be 3 times that. I like the little picture here. After 4 seconds. After 5 seconds. This is why if you jump out of a plane and your chute doesn't open, you're in trouble. What does 9.8 meters per second mean? If you can see me there in the corner, this is a meter stick. Let's see, put it on the ground. I am 1 meter and like 1.7 meters tall. Meter stick, right? If you take one of these, right, this is 1 meter. So after 1 second of jumping out of that plane, you're going to be moving at about almost 10 of these sticks every second. After 2 little seconds, you're now moving at about 20 of these sticks per second. Per second. So it's going to be very, very fast. You're going to hope that chute open. Now, in all this verbiage here, they're talking about a body falling from rest in a vacuum. And this is a key term here. A vacuum is where you yank all the air out of a space. So if we could pull all the air out of our room here, then I could get 2 things to fall at the same rate. Things don't normally do this here on Earth because of air. Air causes friction. If I try to drop a book and a piece of paper at the same time, they will not seem to fall at the same rate. The book goes a lot faster. Why is this? It's because of air, right? And so a lot of people say, well, air is acting on the paper more so than on the book, which isn't really necessarily the case. If I take the book and the paper, I put the paper on top of the book, we can greatly cut down on air influencing the paper. They should both fall at the same rate. And they do, so that's pretty cool. Which one actually feels the greater force of air? It's actually the book, not the paper. The thing is, the paper doesn't have a whole lot of mass, and so what will happen is you just won't have there's not a lot of mass, so it doesn't take a lot of air to influence that paper. Here on Earth, everything falls at this rate. But because there's air, it looks like heavy things and light things fall at different rates. And they really don't. It's just that air is just acting on things. But if we could yank the air out of a certain space, we could prove it. Here I have this tube. It's like a plexiglass tube. It has a little stopper at the top, and it's got a penny and some tissue paper. And so if I turn this thing around like this, you can hear the penny hit the ground before the tissue paper. You see the tissue paper kind of flutter. I hope that you can see what's going on here. The penny gets down there first and it kind of bounces. The paper kind of flutters. Okay. And what I'm going to do is I'm going to try to yank all the air out and show you what happens if I pull the air. It's called a vacuum pump, and I'm going to try to vacuum all the air out of this space. And see if I pull all the air out, and I create a vacuum into this little chamber. So pull all the air out, see if you can tell. The paper doesn't flutter quite as much. Everything gets down at the same time, see? It all gets down there. Penny kind of bounces, so it's hard to tell, but everything should get down there at the same time. If I let the air back in, and we should have more. Oh yeah, see the paper flutters a lot more. It takes its time. So in the absence of air, everything falls at the same rate. Galileo was the guy, allegedly, who had done this. He had done some tests off the top of the tower of the Leaning Tower of Pisa, and he dropped certain things, and he had figured this out. And so you can also figure out that after 1 second, if you're going a certain speed, you should be able to, you will fall a certain displacement. That's something else that should happen. Here again, due to air, it's hard to tell. But this was a thing that was done way before any of our time. So, and here's the thing that I did. Okay. So things usually don't reach the ground at the same time, and that's due to air. So if you jump out of a very, let's say that you're in a plane and the plane's at 10,000 feet, and you have your pack on, and you jump out of the plane at 10,000 feet, and you're falling, you're speeding up that whole time. Now air is pushing up on you, right? But gravity is pulling you down. The force due to gravity is pulling you down. So you are accelerating. But what happens at some point, you reach this speed called terminal velocity. And I ask people, what happens at that speed? And they go, that point, what happens? People go, all the forces are balanced, and so you stop. I'm like, so you're saved, right? That's really not what happens. Eventually, anything falling within Earth's gravity, if it has a long enough time, can reach this speed. This is a maximum speed that something can hit, and different things have different max speeds depending on size, shape, things like this. We would do this lab in class of a coffee filter, and if you drop it here in the room, it will hit terminal speed for a coffee filter within 2 seconds. For the human body, it takes a bit more time. And at terminal speed, what happens is you don't speed up, you don't slow down. All the forces are balanced, so you're on cruise, right? So that's a thing that can happen. Okay. But everything falls at this rate here on Earth. If you throw something upwards, right, then what happens? We'll go up, 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 up. It will stop. It will then come back down. So here's a graph of the displacement of something that is thrown straight up. I'll do this in class where I throw something upwards and I say, describe what's happening. Well, people say it goes up and it comes back down. I'm like, yes. What happens before it comes back down? What happens at the very tippity top, way up here at the top? And it's hard for me to get people to say that it stops. But if something goes up, if you throw something upwards here on Earth, it will go up, 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 and it will have some max height where it will stop. And I will ask people, what is the acceleration of that thing at that max height? And they'll tell me it's 0. And it can't be. If acceleration were 0, it would keep going. Earth is pulling on it, yes. So when it stops at the very top, tippity top, the acceleration due to gravity is 9.8. It's really that the whole way, up and back down. If you throw something, it starts with an initial speed. The initial speed is not 0. So if I take something and I throw it upwards, the initial speed is a non-zero thing because I have to get it going. And as it leaves my hand, what is its speed? It has some positive speed, right? It goes up, 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 up. What does it do as it goes up? It slows down. It slows down, slows down, slows down, slows down. Boom, it stops for a split second at the very tippity top. And then it speeds up again as it comes back down to your hand and you catch it. So the velocity time graph would look like this, where it has some initial speed, it slows down, it stops briefly at the top, and then it speeds back up. And it's coming this way. We usually call going down negative, so that's why the graph crosses over into this negative zone here. What about acceleration in time? Well, it's constant. In fact, what is it? It's negative 9.8. I usually have it negative as it's always pulling on us this way, right? The force due to gravity is always pulling us down. So I always have 9.8 as negative 9.8. So when I work problems, if things go this way, whatever it is, displacement, velocity, I have it positive. So if I throw something upwards, my velocity starts positive. If I drop something, right, what speed does it start with? If you drop anything, what speed does that thing start with? It's 0. And then it would increase in speed going this way. So if I had a graph of something that was falling and I had dropped it, if I drop something, it starts at 0 speed, which means it will start right here, and it's going to pick up speed. So I take my pen and I let it go. It starts at 0, and then as it moves downwards, it picks up speed, so its speed increases. So I'd have something like that. That would be my VT graph for something that I drop. It's going to be in this bottom part because it's going to be negative because it's going that way, and anything and any problems that I do going this way are going to be negative. Okay? About the distance time graph, right? My speed increases this way in the negative direction, right? It's going to speed up. So it's going to start at 0 speed and it's going to, quickly pick up speed, which means for my displacement, what happens, I'm going to, every second, I'm going to cover more and more ground, right? The first second, I'm moving at 9.8. The second, I'm moving at 19.6.